Hello, and welcome to another update on the geologic situation going on in Iceland. It is Sunday, November 19th, 2023. I'm geology professor Shawn Willsey. Thanks for joining me. It is about 9:30 a.m. Mountain Standard Time. That would make it about 4:30 p.m. in Iceland. So thanks again for joining me. I want to express appreciation to all those who have supported what I've been doing with the updates. The comments and encouragement have just meant the world to me in terms of people loving my style of teaching and sort of my approach to this unfortunate situation that's developing in Iceland. I think a lot of the world finds interest in what's going on, both from a human aspect, but also from a scientific and a fascinating worldview. And so hopefully we can continue to be respectful to the good folks in Iceland and have some empathy for what they're dealing with, but at the same time also enjoy learning about how the earth works and the possibility of a volcanic eruption or whatever might take place here. So thanks again. Appreciate all your support, whether it's financial or just encouragement. Much appreciated. The big update for today, what we'll do today is there's not a whole lot going on today over yesterday, so I'll provide a little bit of an overview of what's been going on. We'll look at some of the seismic data and we'll use some of what we learned in our last update about the little beach balls, what we call the focal mechanism solutions. I think there's some interesting applications of that knowledge that we gathered last time. We'll look a little bit, at the data, and then we'll do some question and answer from viewers, which a lot of people seem to enjoy. Felt more like a classroom, more like hopefully an organic, natural discussion. So, there's obviously no eruption at this point, but we're still looking, all the signs are still pointing towards something happening soon. Now, what is soon geologically? Probably within the next few weeks or so. I know we've continued to say that, and we're probably a week or a little bit more into this thing. And that's where our human patience comes into play. We're used to like get it right now, kind of quick service type of society. That's the world we live in. And so if it's not happening, we tend to check out. But knowing what I know about not just volcanoes, but what's happened here in Iceland previously, I can tell you that this is far from being over, that there's most likely going to be an eruption. I can't say for sure. And it's just a matter of both when specifically and exactly where in this region that we've been focusing on near Grindavik. And so let's start with we still have earthquakes that are going on. We'll look at the seismic data here in a second. Let's start though with just maybe the headlines coming in from ruv.ice. So just they've got a nice little bulleted list here. So likely scenario is that an eruption will begin. So you can see that first headline there. So all the indications are still there pointing towards an eruption. The Met Office says that the current sequence of events is similar to the one that happened on the eve of the eruption in 2021. So we're seeing a similar pattern of seismic and deformation behavior. And so, in terms of the scientific community, we're still fixated on this thing. We haven't checked out. We're not on to the next big thing. We're watching this thing closely, and we understand that it can take some time for this situation to evolve and run its full course. So, there was a reasonably sized earthquake near, let's see, how do I pronounce this? Krishuvik. I kind of wrote down the phonetic thing west of Klevervatn, which is a lake. And we'll get to that in a few minutes here. Civil Defense revealed the design exists for the wall. So yeah, they're working on the power plant first, and then also then they're looking to enforce or not enforce, create some sort of structure around Grindavik that could potentially help it out if there is lava flow that occurs in that area. Folks are able to get back into their homes a little bit, which has been great. Some of the residents, and they are working on passing a bill that will help guarantee those people get wages for the next 3 months. So that's good news. So I think Iceland is doing a fantastic job of just dealing with this disaster, dealing with the evacuated people, and just doing all the small things that need to be done in order to make that transition as seamless as possible. So Anyway, so that's from ruv.is. If we go to the Met office, they don't have a whole lot as of right now. They might have an update later. The only thing on here, and you can see that magnitude 3 earthquake there, the little star on the map here, and that was a 3.7. But yeah, they just have this one little update here that pretty much is everything we kind of know. They've had a lot of earthquakes, hundreds of earthquakes over the last 24 hours. The intrusion is still there. The likelihood of a volcanic eruption is high, and an eruption can be possible on a timescale of just days. And so that was actually written today, November 19th. So they're obviously focused on what might be going on there as well. If we look at some of the seismic data, I think there's a fun little exercise we can do here where we can apply some of the knowledge hopefully we gained from my update yesterday when I explained how those beach ball diagrams, those focal mechanism solutions, are generated for earthquakes. So here we have, and this is for 24 hours, and I've got it selected for magnitude 1 and above. There's the trend of seismic data. We've been looking at this pattern for well over a week now. The only thing different between now and a week or so ago is the magnitude of the quakes has dropped, the number of quakes has dropped, but it's been largely at this sort of level for the last 3 or 4 days, I'd say. And if you get in here in detail, it looks like a big line, but there is some clustering going on. There's a definite clustering of quakes near the north end of the intrusion. Then I think there's another cluster of quakes here. If we zoom in a little bit more, and then maybe another cluster here near Hagafell, which is where they've been hypothesizing that the event might take place if we were to have an eruption, that it might be somewhere near here. But if these three locations remain the most seismically active, then they would probably represent the most likely place. Again, the data's changing, everything's in flux. We just kind of have to take it and roll with the punches. But what we're seeing less of now is the possibility, at this time anyway, of an eruption in the ocean. We're just not seeing much seismic activity there, or even something right in or close to Grindavik itself. And so we're not seeing any indications that that's going to happen. That being said, of course, an eruption further up in one of these three clusters would definitely have an impact, most likely have an impact on Grindavik and possibly the power plant and the Blue Lagoon. If this continues, I guess the best three scenarios of these, best solutions, possible outcomes of these three would be an eruption further to the north. The further we can get this eruption away from Grindavik, that would allow possibly some of the lava to flow into some of these other valleys or some other topography up here, and it also would give them a little bit more time if they are able to build some sort of berm or barrier embankment around some of the critical parts of town there. So maybe like the harbor, that sort of thing. Okay, so and then if we move over this way a bit, you can see the swarm of earthquakes that have happened over near Klevervatten, the lake that's over here. This is another system of we have a series of volcanic zones. This is considered a separate volcanic zone. So the big question here in looking at this 3.7 that happened in the last 24 hours would be, well, is this, signs of another intrusion, right? I think that's, if you're in Iceland right now, or even if you're not, this might be a worry that some folks have, is like, wow, we got a cluster of earthquakes over here. We know what's causing this one, the intrusion of magma. Is this indicative of either magma moving over to this area, or is this a complete new magma body that's triggering these earthquakes? And so we might end up with, two eruptive events in different places, which would be, a bit of a nightmare scenario, I suppose. And right now, we just don't see any indication that these earthquakes are related to magma intrusion. In fact, what I'd like to do with you is discuss how we can use the beach balls here. So if we look at a lot of these earthquakes, remember, so on these plots we get the little beach balls. And at this point, if you watch yesterday's update, and if you haven't, you might want to go back and watch my little lesson on how to interpret the beach balls. But this tells us a little bit about how this specific earthquake, in this case the 3.7, it tells us where the fault is. So the fault is either a north-south trending fault, almost north-south, or a, sorry, it kind of moves around when I move on it, or an east-westish trending fault. And because we see these crisscross, this X pattern here, this tells us that this fault movement is strike slip. It's horizontal motion, that the rocks are sliding past each other laterally or horizontally when this specific earthquake occurred. And if we look at some of the other ones there, so that's the 3.7, but let's look at a couple other ones here. So we've got this one here. So this one's, I'd say, mostly strike slip, but it has a little component of opening, a little bit of a extension. So it's a little bit of a normal oblique fault. Let's grab a couple others here. Let's look at that guy. Similar, so no, that's a normal oblique fault as well. This one here, that's almost purely strike slip, that one there. Let's try this small one here, 1.8. Purely strike slip as well on that one. And what I'm getting at here, and this is, again, this is my nosebleed seats. There's one that's mostly normal with a little bit of strike slip motion. I think that a lot of these quakes over here are being triggered. By the magma intruding into this area, we've changed the stress regime throughout the region, right? This magma has forced its way into the Earth's shallow parts of the Earth's crust, and that compressive stress is being felt regionally, and that might be triggering other small faults to move and experience earthquakes because of that change in stress level. And because we're seeing a lot of these as strike slip faults, it kind of makes sense as if you kind of push magma into this zone near Grindavik, that you might push the rocks in other places. They'll move laterally, right? They might move sideways and move away from this new stress that's been imposed by the magma intruding. And so, again, I'm not a seismologist. I'm just probably dangerous with the knowledge I have. But my hypothesis, not a conclusion, would be that perhaps we're seeing a lot of strike slip earthquakes here because of that movement, right? Because that movement is shifting things more side to side. And we're not seeing faults in this area for the most part that are normal faults, that are opening up, that you'd expect to see maybe over here, right? Now, some of these are going to be strike slip ones too, but a lot of these, that's pretty close to mostly normal, pure normal fault with a little bit of sideways motion. We could look at some of these as well. That one's got some strike slip motion as well. You can run this exercise through on your own if you'd like. I'm not saying that all these earthquakes here are normal faults, but a lot of them are dominated by extensional stress as opposed to lateral movement, or what we sometimes call shear stress. So just a fun little thought experiment there, but I would not be worried about these quakes over here being an indication of either a new magma body intruding or movement or migration of this magma body off to the east here. We'll have to see. The 3.7, that the people felt it apparently near Reykjavik, and so that's noteworthy. We'll just have to wait and see. But nothing right now is showing us that this is an area of concern. We're not focused on this area. We're still focused back over here, and that should continue moving forward. So. Okay, so let's go to a few questions that folks had. So again, I just plucked these off of the last few video updates. So I just kind of scrolled through, and when I found a question, I would copy and paste it. And so let's start with this first one here from my French guy. I didn't know I had a French guy, but there I guess I do. Asked if there's a difference between saltwater eruption and lake-like eruption. So I believe they're referring to, if we had an eruption out here in the ocean versus if there was an eruption in some water body. And the answer to that is the chemistry of the water doesn't really play a role in determining the type of eruption that ensues. And so an eruption in the ocean and an eruption in, let's say, a large lake with ample supply of water would largely be the same. Yeah, so I mean, we could go through that whole scenario, but we've talked about it before. The the lava heats up the water it gets vaporized, it turns to steam. That's an expansion process, and it makes it much more explosive. And so you're shredding that lava into little tiny bits. That creates the ash and the rocks that go flying up into the sky. It's making it more of what we call a pyroclastic eruption. Things are being thrown up into the atmosphere as opposed to just lava flowing along the ground there. So hopefully I did okay with that one. But yeah, no real difference there. As long as there's enough water. If you had like a small pond, something like one of these ponds in your town, if the vent opened up here and was exclusively, now that one's really close to the coastline, but let's just say it stayed here, you could get rid of all this water pretty quickly. The lava, presumably you'd have enough lava to interact with this water that would vaporize all this water pretty quickly. I'm assuming this is a pretty shallow lake. And then once you get rid of all that water, the eruption would transition from being somewhat explosive into being more effusive, and eventually it would transition into just a land-based type eruption with lava flows. So, okay, next question from Music 100 Vid. In your opinion, based on the current data at this point, how much warning do you think we would get before an eruption? You mentioned, let's just start with that one. Let's start with one question at a time here. Um, we're going to have to see a lot of things change to probably get to an eruption. Now, that being said, um, a lot of times there's a calm before the storm, and I believe that was the case with some of these eruptive events here. Is that the earthquakes happened, there was the buildup in the ground deformation, and then things got kind of eerily quiet, and then the next thing we knew, there was lava on the ground. Um, and that can definitely happen here as well. We could go from sort of things at a background level to an eruption in a pretty short period of time. And so I wouldn't be surprised. I would expect we need to see earthquakes getting shallower towards the surface. If we have a lot of instruments in place, we might be able to detect gas emissions that would be helpful. So gas emissions, if that data was available, shallowing of earthquakes moving towards the surface, which would indicate the magma bodies moving closer to the surface, and possibly more ground deformation measurements. Those would be some of the indicators I would expect to see prior to an eruption. That being said, we've seen in the past that we can have eruptions at the surface without some of those signs. So if it's a textbook eruption, I'm expecting to see those signs, but I'm also okay with the possibility that it doesn't show any of those precursor signs before it erupts. And then the second part of his question, you mentioned groundwater and hydrology. Is it possible magma could suddenly reach groundwater, causing an unexpected explosive eruption? Yeah, so it's a great question, and definitely here where I live in southern Idaho, we have, and I'll spare you zooming there on Google Earth, but we have landform features here in southern Idaho, large, shallow, broad craters in my landscape where I live here that have been formed by lava interacting with groundwater. It does create explosive conditions. What it depends on, though, is that ratio, right? How much groundwater, how much lava is there, and can the groundwater get to the lava? Sometimes what happens is the lava rises, it can seal off the groundwater from infiltrating and mixing with it, and if it creates an effective barrier, then you don't get a explosive eruption caused by the lava and the water interacting. Other times, if you have high permeability in your rocks and materials, or a lot of groundwater movement and maybe a high volume of groundwater flow, then and or a smaller amount of lava, then you might be able to get that ratio just right that you do create explosive conditions. And there are other places in the Icelandic landscape as well, where they've had explosive eruptions. There's one I can think of. The question is, can I find it? I know it's part of the Golden Circle. Oh, there we go. It's Kedig. Kedig. I don't know how to pronounce that exactly, but this pit in the ground right here is essentially that, has that sort of history that it was a water lava interaction that blasted out probably this series of craters here, at least these three. This one's just deep enough that the groundwater now percolates into it and fills it up and makes a lake there. So anyway, good question. Let's see, next one from Sailor Gear. When magma is moving up through rock layers, is most or all of the movement due to forcing its way through existing fissures and breaking rocks to form new fissures, or is any of the movement due to melting through the existing rock layers? I imagine melting rates might be relatively low due to the high insulation effect and heat capacity of the rock, but is such melting through negligible or non-existent compared to moving through fissures? That's a great question, very well written. Yeah, very well thought out. My understanding is there's not a whole lot of melting that, especially in this case, because you're bringing magma. As that magma comes up in Iceland, what kind of rock is it moving into? In this case, on the Reykjanes Peninsula, it's moving into basalt, essentially the same, the 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 composition of the magma and the composition of the rock that the magma is moving through is essentially the same. There might be small variations here and there, but it is mostly the same. It's the same flavor. And so, because these rocks have a high melting temperature, they won't melt. And you would need to put magma in contact with that rock for a long time, whatever a long time is, probably more than just the contact itself, in order to completely melt that rock. And so the other thing to think about as the magma comes up and is in contact with the rock is it cools very quickly up against the rock. Just like when lava is at the surface, the top layer tends to crust over because it's in contact with the much cooler air. And when it cools like that, it creates a thin little skin. And being a really good insulator, it can keep that magma. So it's essentially forming a barrier between the high temperature molten magma and the country rock, the rock that surrounds it in this case. And so, yeah, really good question, but I would say it's negligible. Like it doesn't really melt much. Now that being said, when we have like lava tubes can insulate really well, and they can thermally erode, so they can melt the rock, and it can melt, rock that's of the same composition. But you got to have the temperature staying really hot for you know an time, like some component of time, days, weeks, months, and then you can melt the rock, but it's not wholesale melting of the rock. It's localized, it's incremental, and so it's a little bit slower than you might think. Good question though. Abe Gilbert, is there a way science or technology can induce the eruption event to relieve the pressure and allow humanity's work to carry on? Yeah, like let's just get the magma that's down there and just squirt it out into some valley or out into the ocean somewhere. If feasible, it could also give engineers possible directions too for the release. Stay away from the geothermal plant. Well, it's a good thought, and you're not the first one to consider it. It's never been done. It makes sense in your head, and then when you start to kind of think about it practically, at least, and I'm not an engineer, it's just not possible. You're looking at a huge amount of magma, even in this event, which is, in the world of volcanoes, this is not a super large amount of magma, but it's still large. And you're trying to relieve all that pressure or drain out that magma through one point, and it just doesn't work that way. The magma is buoyant. We don't know exactly where the magma is in the system. We don't know where exactly the pressure is highest. So the first thing you'd have to figure out is like where exactly are you going to put a hole in it. And like I've mentioned before, the analogy that works in my brain is it's essentially like taking a hot air balloon and putting a pinhole in it. You're just not doing enough. You'd probably have to put a lot of holes into the system, drill a lot of holes into the ground, and or yeah, I just don't know any instance where it works. Maybe there's someone out there smarter than me that can crunch the numbers and all that. It's a theoretical concept that just doesn't have any practical application, I think is the best way to put it. So for now, until we figure out how to do that, and we might not ever, we will be stuck with the uh, older method of just monitoring, letting the eruption occur where it occurs naturally, and then mitigating its effects to humanity as best we can. So maybe not the answer you want to hear, but that's kind of where we're at right now. Let's see, next question. Are there any chance that seawater gets into the magma chamber through the fault line? Another good question. The seawater is obviously down here along the coast. The water that sits underneath this area is mostly freshwater. There may be some seawater. Seawater and freshwater don't mix well together. They actually have density differences, and so they don't blend well. But the question's asking if the seawater gets into the magma chamber through the fault line. Oh, the other thing to consider about, and I don't know what the fault line is they're thinking of. Maybe it's any of these fractures and cracks that we're seeing happening in the community here. But faults are frictional surfaces, right? So fault, let's be careful here because I've mentioned in previous episodes we've talked about fractures. Now fractures or cracks or openings, right? A fracture has a certain um, aperture of opening. You might have a 1 meter wide fracture, you might have a 1 centimeter wide fracture. But fractures, especially in Iceland, are not necessarily faults. To be a fault, you need a fracture, right? But it needs to have movement. And most faults tend to have it's stress that's building up that allows the two sides to slide past each other. And so for that reason, faults are not always good pathways for fluid. Now, they can be. We can get fluids moving through faults. And this is actually where I don't want to make this too much of a tangent or a rabbit hole, but miners back in the day realized that faults were good places to look for ore deposits, gold, silver, copper, because they're pathways for fluids, usually hot fluids, what we call hydrothermal fluids, to move through the rock, maybe not up, but move through the rock and then precipitate or deposit mineral material. But other times faults can be inhibitors to fluid flow. And I've worked in the groundwater industry before teaching, and it's tricky because some faults have enhanced permeability and allow fluids to move through it more readily, and other faults are impermeable or largely impermeable. They impede fluid migration through the rocks. And so seawater probably is not going to travel through the fault line and get into the magma chamber. So I think maybe the crux of their question was, is there a way for the ocean water to get into an inland location along the fracture system or faults that might be there? And I would say the answer to that's no. That's a very unlikely scenario, but a really good question, good thought question. Gary Doty or Doty, do you think that the ground settlement around the town of Grindavik has less to do with magma intrusion and more to do with the seismic activity settling the existing non-native fill? So I think what he's referring to there is the fact that when they constructed the town, they obviously, well, we don't know this for sure, but in any sort of construction scenario, there's a certain amount of grading that needs to go on. You've got to like level out some land, you've got to move some fill material from one location and maybe fill a little depression. There's compaction that goes on. There's a certain amount of preparation that takes place prior to building construction. And his question is asking then if the settlement, maybe the subsidence of the town has less to do with what the magma body's doing and more to do with the earthquake causing things to sink and shake a little bit. And he's actually onto something there. I think right now we don't know for sure. I think the rate though that we saw, whoops, sorry, saw the town sinking in, a meter or so over a week. That's very likely due to some of the things I've showed you with the magma intruding. You get that graben or that depressed area above the tip of the dike caused by the stress conditions there. So I would say it's probably mostly due to the magma intrusion, but we might be seeing enhanced subsidence or settling of in the town, possibly due to some collapse of some of the fill material. So I can't completely discount that's a possibility that there's a little bit of subsidence in town happening for that reason. So really good question. Some of these answers to a lot of the questions we have right now will be kind of post-mortem autopsy kind of questions. Like we got to wait for the whole thing to run its course, and then we'll have the perspective and the knowledge to look back and be like, oh, that's why we saw this happening, and that caused this. But in the moment, it's a little bit trickier to do that. So, okay, a couple more questions. Every time you show the wider satellite view, I notice the diagonal features on the ground to the east that echo the earthquake activity diagonal. Diagonal you overlay on the current active area. I hope that makes sense. I think I know what you're saying. They look like mountain ridges waves getting longer as they move east. Are these past eruptions? If so, does it make sense to assume eruptions will continue moving west along the peninsula and at a similar diagonal over time? Okay, I think I get your question. And so I believe what this person's asking is when we look at the topography in Iceland, and let's just get rid of all the little fun icons here. Um, just make that smaller. So the topography, we see these ridges, right? We see these pronounced northeast, southwest ridges that run across the landscape. As you get further into the country, maybe take the roads off, it gets a little messier. We start getting singular, larger volcanoes that are capped with ice. And of course, the hotspot sits more over here. In fact, the hotspot's kind of like right in this area. Um, and so her question is, let me go back to the question. Oh, is it makes sense eruptions will continue moving west? No, we'll probably continue to see eruptions in this region on the Reykjanes Peninsula. We're going to see more eruptions out here for sure, where the mid-ocean ridge comes ashore. And in fact, they had a pronounced phase of eruptive activity here 5 to 800 years ago, something like that. We're seeing it right here. Whoops, sorry. We're seeing it here today. And these areas over here, we would expect to see them. Now, these are bigger landforms. If you come over here, we've got bigger mountains and hills because a lot of these erupted, excuse me, beneath ice. So when the whole country was covered in ice, we had a lot of eruptions there, and those built up bigger landforms. If you watch the video I just posted yesterday on Tuyas, I talk a little bit about that. In fact, that video was shot right here, looking at this ridge here and then looking across the way at another one over there. This area probably is a lot of newer land, and because we're seeing these more like lava. These are obviously lava flows that spilled out onto just land. There was no ice here at the time of these eruptions, right? But this thing erupted when there was ice, and some of these hills here erupted when there was ice. So I hope I answered her question. Um, yeah, they are past eruptions as you go to the east. Does it make sense to assume that they'll continue to move west? No. And so I think she's also picking up on the fact that, hey, the last couple eruptions were over here, but now we've got this potential eruption happening here. But if you look at the trend from the last three, it moved northeast, right? It went from here to there to there. So, I mean, if you were to ask someone a month ago, where might the next eruption be? It's only three data points, but you might have. It almost looks like it was a propagating dike or fissure that's opening like a pair of scissors to the northeast. So you might have guessed over here near Kelir, this tall cone-shaped mountain here, that was going to be the next location of the eruption. But in fact, it jumped to the west. So yeah, it's a complex system, somewhat, I wouldn't say unpredictable, but difficult to forecast exactly where some of these eruptions are going to take place. So great question. From Chris Percival, if there is an eruption at Hagafell, what is the most likely direction of the lava flow? Well, that one's a little bit easier to deal with, and I know there's other folks out there that have really good, even our seismic one. I think when you zoom in, it has some contour lines. If we get in here and take out, oh, let's take out the earthquakes. Let's just do that. So yeah, this might be one of the better views. And I know some of you are like, hey, why isn't he going to the map with the great contour lines? I don't have it ready right now. So, but here's Hagafell. Here's the town right here. And maybe we'll go back to Google Earth. That provided a little bit more color, I suppose. So Hagafell is here. So if we get an eruption here, anywhere more or less along the system, we can see where the lava went in the past, and that's this kind of green mossy terrain you can see here. The lava is going to head south towards the coast. So if it's near Hagafell, that's that's rough. But there's so many little variations here. Like if it maybe the vent opens up over here somewhere, right? The vent opens up here. We're going to get lava flows flowing to the south, and some will come into the east part of town. Excuse me, undoubtedly, and maybe into the harbor, which is bad news. But there's a good chance a lot of them go this way, right, off to the east of the town. Um, so much of this depends on exactly where that vent opens up, and really a difference of just in some cases maybe tens of meters one way or another as exactly where it's going to go. But to answer your question, if we get an eruption in this area, it's going south, maybe more southwest, more due south, but some component of south that's headed towards the coast. It's going to impact at least parts of Grindavik. It's just a matter of how much and where exactly. So that's one of the big questions we have out there. So from Meredith in Sierra or in Sarah, what are the chances that a major eruption in this location ends up causing the kind of major climate change that caused the climactic catastrophe from the year 536 when it's thought that Krakatoa in Indonesia blew up and much of the earth was covered in ash, long enough to block out the sun, cause widespread drought, drops in global temperatures, crop failures, famine, etc. Wow, Meredith, you're just bringing me down on a Sunday morning. It's already cloudy and gloomy here in southern Idaho. I'm really into the history of the Middle Ages, and this event had, yeah. So Krakatoa's eruption in Indonesia, um, and I thought that was in, I can't remember what year it was. I don't know if you've got the year right, but we'll assume it was something like that. Um, yeah, big eruptions like that, though, are going to need different types of volcanoes, and we don't have the right type of volcano here. We have a system here in the Reykjanes Peninsula where we have mainly basaltic magma. Basaltic magma is high in temperature, it's low in viscosity, which means it's runny. That's good news because it doesn't trap gases. So the magma, once it gets to the surface as lava, a lot of that gas is going to dissipate into the atmosphere. Um, what we don't want to see is a magma system that traps gases, because when it traps gases and it gets closer to the surface and the pressure is reduced, it explodes. It's like an exploding bottle of soda. And that's your more violent Krakatoa, Toba in Indonesia, um, Yellowstone type of eruptions. So we're not going to see that here. This eruption is not going to produce any of the things, well, most of the things you mentioned there. Could it produce ash? Only if it's in the ocean, and even then, I don't think it's going to produce that much ash. Is it going to block out the sun? No. Is it going to cause widespread drought? No. Drops in global temperatures? No. Crop failures? No. Famine? No. So will this event, if it occurs, and let's assume even like a worst case scenario with this eruption, um, it's going to be a historic eruption possibly to modern Iceland's history in terms of its impact. I could argue that even without erupting, it's already, I think, the biggest disaster in Iceland, most costly disaster since the eruption on Heimaey in the 70s. So it already is having an impact in Iceland, but in terms of global history, and no, not at all. So not a worry there. Stephen Hill, let's see. Iceland sits on the mid-Atlantic ridge and over a hotspot as well. The distribution of earthquakes seem to suggest that this is the hotspot that's causing the recent event, or is that just too simplistic? Great question, Stephen. And this is something I did. I think I do have something prepared on. Oh, maybe I don't. I thought I had a diagram there. So we know we have the plate tectonic boundary that comes ashore here. And I've shown that map previously, but it basically, the plate boundary comes ashore on the southwest part of the peninsula, rolls right through this area, and then heads across the interior of Iceland, and then exits North Iceland somewhere over here. So there's the plate boundary. So more or less half of Iceland sits on the Eurasian plate, and half sits on the North American plate. And that is what causes, excuse me, that's what causes a lot of the earthquakes in Iceland. It's also what causes a lot of the volcanic activity. As he mentioned, though, in his question, there's also a hotspot that sits underneath Iceland, but the hotspot's over here. So the entire country, the entire island, is not sitting over this plume of magma coming from deep within the earth. The direct location sitting above the hotspot is this area here. And I know I don't have like a perfect circle there or anything, but roughly here, right, roughly, this is the Vatnajökull ice cap, the biggest glacier in Europe. And it sits, if I had to just leave my cursor in one place, I'd probably put it right about there. And I'm probably pretty close with that. Um, so getting back to his question, the hotspots hundreds of kilometers away from where we're seeing this latest volcanic activity. And so it's thought that the volcanic activity we're seeing here is mainly a result of plate motion, that the plates don't move for a long period of time, but stress builds, and then the plates move apart. That generates earthquakes. And by moving the plates apart, that is extension. That takes pressure off the underlying upper mantle, and by taking pressure off of that, that triggers the generation of magma. And once that magma forms, it rises to the surface. Maybe it makes its way all the way to the surface and we get an eruption. Maybe it rises close to the surface, becomes neutrally buoyant, if you will, and then stays there for a while and cools and crystallizes. So I hopefully that makes sense a little bit. So now the only little thing I'll add to that is the plates are moving here apart, and the hotspot's over here, but the hotspot isn't just like a perfect like circle. It has little, you might have little branches that come off of it. But I think most people would agree with me that the Reykjanes Peninsula is its volcanic activities related mainly to tectonics and plate motion in that area. Good question. I think our last one here is this, and I have a fun little animation I'm going to throw in here as well. So there's a fun lesson coming at the end that you might really enjoy. Um, so hang in here, folks. Okay, from Deborah, is the Pacific Plate growing? And she's referencing some point on one of the previous videos where I showed the plates. Which way is the Pacific Plate moving, or is it growing in size? Likewise on the South American Plate. So the Pacific Plate. Let me go back to Google Earth here and let's head over to the Pacific real quick. Let's use Google Earth, zoom across here, kind of zoom out, set north to north, bada bing, bada boom. There you go. So is the Pacific Plate growing? And I mean, gosh, in Google Earth, it's even hard to get the whole plate on here. So the Pacific Plate, the edge of the Pacific Plate runs along something like this from New Zealand up through Indonesia, the Philippines, Japan, Northeast Russia, Alaska, like that. So the plate is moving to the northwest, and the little chain of hotspot islands here in Hawaii nicely shows that direction. So the plate's moving to the northwest, more or less in line with this chain of islands here. It is subducting or sinking beneath another plate along a huge area in the West Pacific over here. So from Alaska down through some of those places I just mentioned down to New Zealand, it's sliding and sinking beneath other plates because it's more dense, because this is all made out of dense ocean crust, basalt, and it's more dense than the plates that it's running into, and so it's sliding beneath it. But at the same time, if you come back over here towards South America, there is a different plate boundary that zigzags through the ocean here, and this zigzagging plate boundary is a divergent plate boundary. So here the plates are actually spreading apart. So this is the other edge of the Pacific Plate. This is the Nazca Plate, and this is a plate that's being shoved to the east where it collides with South America. And notice you get this deep ocean trench over here, and that creates a series of volcanoes and mountains here we call the Andes. So this plate boundary is creating new crust, right? So this is allowing the Pacific Plate to grow. So to answer your question, the Pacific Plate is growing if we just look at what's happening here, right? More magma comes up, the plates push apart, and the process continues. But at the same time, at the other edge of the plate, this is where the plate's being recycled, if you will. It's sliding back into the earth. So the question is it growing? Well, if it's generating more crust here at this plate boundary than it is over here, then it would be growing. Just like your bank account will grow if you put more money into it than you spend, right? But that's not what's happening here. The plate is actually moving faster at the subduction zone than it's growing back here. And so the Pacific plate, to answer your question, is actually shrinking. It's getting smaller. This ocean basin, which is the largest on planet Earth right now, is in the process of getting smaller. And so I think that was the part of your question there. I told you which way it's moving. It's not growing at all. And to illustrate this, what I thought we'd end with here today, team, is a fun little graphic that I have. I use this in my classes too. And this is something called the Wilson cycle. So this is a nice summary of how plate tectonics works um, from start to finish. Now, this is highly simplified. This does not mean that every single continent and plate evolves fully this way, but we do see this looking back in Earth's history that this is a common theme. So if we start with the continent, so the brown kind of mushroom shape there, you can see the mountains and you can see the ocean. So that's our continent and our continental crust. The dark layer here in the middle, that is the upper mantle. Okay, so that's the upper part of the next layer. And then the orange layer at the bottom is the asthenosphere. The asthenosphere is a weird layer within the Earth because if you do the right things to it, you can melt it easily and make magma. And the two things that will generate magma here are to either make the rocks above it thinner, so if pressure is taken off of it, that will generate magma, or if you shove rocks down into it that contain water, that will generate magma as well. So what we're going to see is this big continent is going to start to rift. And so you can see at the surface, we've got lots of little faults. We've formed a graben, right? So we formed a valley, a rift valley. And the great thing about this animation is you can go somewhere on planet Earth and see parts of a Wilson cycle taking place everywhere. So where would we see something like, let me get it paused at just the right spot, like maybe like this, where we have, maybe we'll take it back just a skosh, like that. Where could we go on planet Earth where we have a big valley on a continent, low in the middle, higher on the sides, where volcanoes are also erupting down the center? A good place to see that would be in Eastern Africa, places like Ethiopia and Kenya. So if you allow this to happen, that magma starts to rise towards the surface. It's less dense than the rocks around it. It makes its way to the surface and it starts erupting. So there's our eruptions happening right there. Now we have a volcanic valley, a rift valley, but it's on land, right? Well, what kind of material is this erupting? This is erupting basalt, and basalt is a very dense, heavy rock. So as we start erupting that basaltic lava at the surface, that will form ocean crust. Basalt is ocean crust, essentially. So now notice we've torn apart this continent. We've separated it into two distinct land masses. This would all be continental crust, or what we might call granite. But now, at the leading edge of these two continents where they're separating, we're adding, through volcanic activity, basalt, or ocean crust. And because basalt and ocean crust is dense and heavy, it sags, it sinks, it depresses, and that allows the ocean to inundate that area. And so now we have a nice, thin, narrow, linear seaway. And you could think about places on the Earth where you see that, like the Red Sea or the Gulf of California in Mexico. So we let that go. So now we're creating an ocean basin. This continent has been completely rifted or separated. You might think of it as Pangea breaking apart. And we have an ocean basin. This is how all ocean basins on planet Earth form. But over time, what can happen is, remember what we have here is we have granite or continental crust, which is very buoyant. And then we have this black layer here, which is basalt or ocean crust, which is very dense and heavy. And they're sutured together here. But over time, this basalt is going to get cooler. It's moving further away from the volcano that produced it. And the density contrast between it and the granite or the continental crust becomes greater and greater. At some point, it actually detaches and starts to sink underneath. So for now, the ocean basin gets bigger, right? The ocean, as you've been seeing it grow, gets wider and wider and wider. It's growing. But now what's happening over here on this left side is we're going to allow this detachment to take place between the continent and the ocean. So in the beginning, we just had two plates, right? Everything to the left or the right of this mid-ocean ridge. But now we're going to turn our two plates into three plates. So now we've start creating a subduction zone, one plate diving beneath the other over here. And now we actually have three plates. We have the continental plate here. We have this subduction zone, which is a boundary. We have this second plate here that's mostly ocean basin. And then we have a third plate that goes from this divergent boundary, this mid-ocean ridge, all the way across the ocean, and it also includes the continent. So this is all one unified plate over here on the right. But here's my point. The point is that as soon as subduction begins and one plate starts diving beneath the other, the ocean basin starts to close because this process is faster and outpaces the spreading pace here. Notice we're generating magma over here. We're generating a series of volcanoes and mountains along the coast. So this is similar to the Andes in South America. It's similar to the Cascades in North America. And so we're creating that series of, and so basically now the ocean basin gets smaller. Now we're watching all this play out in a 1 minute video that I'm drawing out with narration, but this would be hundreds of millions of years in terms of actual the time component here. And now you might guess like, well, what's going to happen when this divergent boundary, this mid-ocean ridge, when it gets to the trench here at the subduction zone, what's going to happen to it? Well, let's see. It's still ocean crust. It's going to sink beneath the continent. And now what's happening is that same continent that was rifted away from this other half of the continent, now we're bringing those two continents back together. We're closing this ocean basin that had formed previously. And as these two continents collide, because they're both made out of continental crust, which is incredibly buoyant, neither continent sinks down beneath the other, but instead we get uplift, we get huge mountains. Right here, this would be like the Himalayas or the Alps, and that more or less completes our Wilson cycle. And if you can kind of imagine us going back to the beginning, where we just started with a big continent, that's where you also kind of end, whoops, the Wilson cycle. If I can find where I was at there, something like that. And then the mountains would get eroded, on and on. So hopefully you had fun with that. I use this in my historical geology class when we kind of do a deep dive into plate tectonics to explain how things evolve over time. So kind of long-winded, but hopefully that was helpful in you understanding plate movement and plate motions globally on planet Earth. So you can find this on YouTube, just Wilson cycle. It's a great little animation, very helpful. So I think that's it, team. Hopefully we did some good work here. We did some good learning. Hopefully I addressed your questions as best I could and provided some perspective and insight. Appreciate your support and your continued encouragement. Thanks so much. I will be with you probably tomorrow. We'll see what tomorrow brings. If there's another batch of questions, you can always put those in all caps in the comments. That's an easy way for me to see those as I'm kind of scrolling through. If there's a lot of good questions coming in, I can do another update similar to today. Obviously, if something more substantial happens geologically or otherwise in Iceland, then we'll turn our attention to that. So for now, have a great day. Thanks for joining me and be well.